So, why would we choose to integrate a DSP into a motion control system? DSPs were first incorporated into motion controllers in the early 1990s. They offered the ability to handle complex motion profiles with dedicated processing power. More recently, DSPs have gotten better by offering more in terms of faster processing speeds and generally more functionality in the space of a small IC. This, in turn, has made motion controllers, as well as drives, smaller and packed with more capabilities. By using MATLAB and Simulink, this course examines the classical control system strategies, such as PID control, feed-forward control, and cascade control of electrical drives, which are widely used in current practice. Vector control techniques are well established for controlling AC motors, and most modern high-performance drives now implement digital current control. In these systems, the achievable control bandwidths are directly related to the speed at which the computationally intensive vector control algorithms and the associated vector revolutions can be implemented in real time. Because of this computational overhead, many high-performance drives now use digital signal processors, DSPs, to implement the integrated motor and vector control systems. DSPs are specialized microprocessors used when real-time processing of large amounts of digital data is required to implement complicated control algorithms. The inherent computing power of the DSP allows for very fast cycle times and bandwidths for closed-loop current control. The current control scheme for these machines also requires a high-precision pulse width modulation, voltage generation scheme, and high-resolution analog-to-digital conversion ADC for the measurement of the motor currents. In order to maintain smooth control of torque to zero speed, rotor position feedback is essential for modern vector controllers. Therefore, many systems include rotor position transducers such as resolvers and incremental encoders. The Texas Instruments TMS 320LF2407 DSP controller is a programmable digital controller with a C2XX DSP central processing unit as the core processor. The LF2407 contains the DSP core processor and useful peripherals integrated onto a single piece of silicon. The LF2407 combines the powerful CPU with on-chip memory and peripherals. With the DSP core and control-oriented peripherals integrated into a single chip, users can design very compact and cost-effective digital control systems. This DSP controller offers 40 million instructions per second performance. This high processing speed of the CPU allows users to compute parameters in real time, rather than look up approximations from tables stored in memory. This fast performance is well suited for processing control parameters in applications such as notch filters or sensorless motor control algorithms, where a large amount of calculations must be computed quickly. The LF2407 contains several control-oriented peripherals on board. The peripherals on the LF2407 make virtually any digital control requirement possible. Their applications range from analog to digital conversion to pulse width modulation generation. Communication peripherals make possible communication with external peripherals, personal computers, or other DSP processors. The LF2407 is used as the controller to implement speed control of the PMSM system. 3 input channels are selected to read the 2-phase currents and the resolver signal. The DSP output pins, PWM1 to PWM6, are used to supply the gating signals to the switches and form the output of the control part of the system. The control program of the PMSM has one main routine and includes 4 modules. The overall control implementation process can be summarized in three main steps. The Simulink file is used to test and optimize the controller through simulation before its deployment on the selected hardware. Once the control design is ready, the control input and output are substituted by the related MCU peripherals, which are given in Simulink as block sets. According to the peripheral requirements, it may be necessary to edit the data type of the signals. Finally, the overall scheme, controller, and I/O block sets can be deployed on the MCU, that is, translated into binary code and uploaded into the MCU. This lecture is only an introduction about the real-time PMSM motor vector control technique implementation using digital signal processors.